Welcome everyone for today's class. In this class, we are going to discuss about redox titrations. In previous classes, we were discussing about titrations, types of titration, and terms used in the titration analysis, and so on. In types of titrations, we saw there are some types of titrations. They are acid base titration, redox titration or oxidation reduction titration, complexometric titration, and precipitation titration. Already we have discussed about acid base titration in the last class. In this class, we are going to discuss about redox titration. What is redox titration? This redox titration, it includes all reactions involving change in oxidation number or transfer of electrons among the reacting substance. The standard solutions are either oxidizing or reducing agents. The principle behind this redox titration is the oxidizing agents are potassium permanganate or the potassium dichromate, iodine, etc. These potassium permanganate, potassium dichromate, iodine, they are all principal oxidizing agents in oxidation reduction titrations. In this oxidation reduction reactions, oxidation and reduction take place simultaneously. So that is called redox reactions. We know already what is redox reaction. We should know about redox reaction. Redox reaction means when in the reaction takes place both oxidation as well as reduction reactions. We know what is oxidation and reductions. That is, if it is addition of oxygen, if the reaction involves addition of oxygen, then it is called oxidation. If the reaction involves in addition of hydrogen, then it is reduction. And also we can define in another way the oxidation and reductions. If the loss of electrons, if the reaction involves loss of electron, then it is called oxidation reaction. If it involves gain of electrons, then it is called reduction reactions. Now we know what is oxidation and reduction reactions. Now we shall move into what is the principle behind redox titration. In redox titration, the principle of redox titration is when a titration involves a change in the oxidation number of the reacting species, that is, if it involves transfer of electron from one reacting substance to the other, then it is known as a redox titration. In redox titration, there is the change in the oxidation number of the reacting species. It may be the increasing, so there is the change will be increasing in one reagent and the decreasing in the oxidation number decreasing in the another reagent. So this is called oxidation reduction titration. Say for example, the titration between potassium permanganate and ferrous sulfate, and the titration between potassium dichromate and ferrous sulfate, and the titration between ceric sulfate and ferrous sulfate, and so on. So we can give so much of examples for redox reaction titration like this. In the titration between potassium permanganate and ferrous sulfate, if we take in this potassium permanganate titration, here the manganese present in the potassium permanganate gets here in the titration between potassium permanganate and ferrous sulfate, here the potassium permanganate undergoes a redox reaction and ferrous sulfate undergoes oxidation reaction. That means if the potassium manganese present in the potassium permanganate reduced into, that is, so the addition of electron is taking place in manganese and the loss of electron is taking place in the ferrous ion into the ferric ion. Let us take an example and we'll discuss. So now we'll consider the titration between ferrous sulfate and ceric sulfate. In this titration, electrons are transferred to cerium 4 plus from cerium 2 plus as shown below. Here, so Fe2 plus, that is ferrous ion, gets oxidized and leaves one electron and releases one electron, and the ceric ion, that is Ce4 plus, accepts the electron which is given by the ferrous ion and it becomes into the Ce3 plus. Therefore, here Fe2 plus undergoes oxidation, that is ferrous ion undergoes oxidation reaction, ceric ion undergoes reduction reactions. When we sum up these reactions, we are getting Fe2 plus Ce4 plus gives Fe3 plus, that is ferric and cerous ion, that is ferrous plus ceric gives ferric and cerous ion. Hence, cerium 4 plus is oxidizing agent. It oxidizes Fe2 plus to Fe3 plus, getting itself reduced to Ce3 plus. Therefore, here Fe2 plus undergoes oxidation reaction, but Fe2 plus itself, here Fe2 plus is oxidized by the reagent Ce4 plus. So the Ce4 plus is used as oxidizing agent. So we shall discuss oxidation, reduction and oxidizing agent, reducing agent by using an example later. Now we shall discuss the equivalence point or the end point is determined in two ways in redox titration. The equivalent points or the end point is determined in two ways. So one is the potential of the system changes abruptly in the neighborhood of equivalence point. In our example, that is cerium 4 plus, so we had Ceri4 plus solution to a given volume of Fe2 plus solution. In the neighborhood of the equivalence point or an abrupt change in the potential of the system will be noticed. So here if we plot the EMF of the system against the volume in milliliter of the ceric solution, we get a curve as shown in the figure here. Near the end point, there is a sudden change in the potential of the system. Here it is the end point. In this end point, there is the sudden change in the potential. The potential is we have taken in the y-axis. So when we plot the graph between the EMF change and the volume of the ceric solution, we are getting, that is volume of ceric solution, that is volume of the titrant. So it gives the end point. So end point is determined from the sudden change in this peak. So this is the one method to determine the end point of the titration, that is redox titration. The another method to determine in the end point of the redox titration is by using indicators. Here we can use indicators to determine the end point in redox titrations. The indicators used to determine the end point in redox titrations are called redox indicators. If you use the indicators, To find the endpoint in the redox titration, those indicators are called as redox indicators. The redox indicators that indicate the sudden change in the oxidation potential in the neighborhood of the equivalence point during a redox titration. During the titration, these indicators also oxidized or reduced. The oxidized from so that is the oxidized form will have one color, while the reduced form will have a different color. Here the indicator reduced as well as oxidized, and the oxidized form of indicator has one color and the reduced form has the another color. Therefore, at the end point in the titration there will be a color change. So here if you take the oxidized form, which accepts the electron and goes into the reduced form. So oxidized form has one color and the reduced form has another color. For example, diphenylamine is a redox indicator used as a internal indicator used for titration of Fe2 plus against potassium dichromate. It used as 1% solution in concentrated sulfuric acid. The endpoint is the appearance of intense bluish violet color. Therefore, so we can determine the endpoint of the redox titration by using indicator also. So there are two major methods to identify the endpoint of the redox titrations. They are, the one is by using the potential, by drawing the potential change between the volume of the titrant added, we can get the endpoint. Otherwise, we can get by using indicator like acid base titration in volumetric analysis. Here then another example, ferroin indicator, so which is given in the figure 2, is used when Fe2 plus is titrated against cerium 4 plus. We have taken example already to discuss. In sulfuric acid medium, the endpoint is the change of color from red to pale blue. Here given in the equation. In this, the complex of Fe2 plus with the ligand orthophenanthroline is called ferroin. Its formula is PH3Fe2 plus. The complex ion in the ferroin undergoes reversible oxidation reduction reaction as follows. Here in this, if it is in the ferric form, in a complex form, it is in the ferric form, it is pale blue, and if it comes into the ferrous form, it becomes a red color. The structure of the ferroin is given here. Here the structure is given for the ferroin, that is in the red color form of the ferroin complex. So therefore, to determine endpoint of the redox titration by using indicator, we can identify the endpoint of the particular titrant by differentiating the different color in the taken solution. Now we know what is principles behind redox titrations, and we have discussed this with an example. What are the methods to identify the endpoint in redox titrations? Now we shall discuss some of the reagents used in redox titrations. There are two reagents we are using in redox titrations. One is reducing agents, another one is oxidizing agents. Here I have given some of the examples for reducing agents. Some of the reducing agents in ferrous salts are ammonium iron 2 sulfate hexahydrate, that is more salt, and the another ferrous salt is iron 2 ethylene diamine sulfate, that is O salt. And another example for the reducing agent is sodium thiosulfate pentahydrate and arsenic trioxide, that is arsenous oxide As2O3, and another reducing agent we can use in redox titration. sodium oxalate and oxalic acid dihydrate, and titanium trichloride. So these are all some of the reducing agents we are using in redox titrations. And here given some of oxidizing agents used in redox titrations. For example, potassium permanganate. This potassium permanganate especially used in, if you are using oxidizing agent in redox titration, that is potassium permanganate. If the potassium permanganate is the oxidizing agent in redox titration, those titrations are called permanganometry. And if you are using ceric sulfate or ceric ammonium sulfate, those titrations called as serimetry. If you use potassium dichromate as oxidizing agent, then the redox titration is called dichrometry. And if you use iodine in redox titration, that is iodine is used as oxidizing agent in redox titration, then these types of titrations are called iodometry or iodimetry. If you use potassium iodate in the redox titration as a oxidizing agent, that is called iodatimetry. And if you use potassium bromate, that is called bromatimetry. Therefore, in redox titration itself, we have the several types by using by with respect to the using of the what type of oxidizing agents we are using. If you use KMNO4, that is permanganometry, and if you use potassium dichromate, that is dichrometry. If you are using ceric sulfate, then that is serimetry, and if you use iodine, and it is called iodimetry or iodometry, and so on. Therefore, redox titration itself we can categorize into the several types. But in our syllabus we have only the permanganometry, iodimetry, and iodometry. Now we shall take an example for permanganometry. Here I have given an example for the permanganometry, that is the reduction of potassium permanganate by iron 2 sulfate in the presence of dilute sulfuric acid. Here two reactions are takes place during redox titrations. One is oxidation, another one is reduction reactions. In this titration, that is potassium, the titration between potassium permanganate and iron sulfate. Here in the potassium permanganate, MnO4 minus becomes into the Mn2 2 plus. In MnO4 minus, the manganese is in, that is 7 plus form. That 7 plus form comes into the 2 plus form, which means it adds 5 electrons and come into the Mn2 plus form. Therefore, so this type of reaction is called reduction reaction. The reagent which undergoes in this redox reaction is called oxidizing agent. So to balance this equation, so automatically we need to add 8 protons and gives Mn2 plus and 4 water molecules. And to balance it electrically, 5 electrons is needed on the left hand side, so that we have added the 5 electrons in the left hand side here, and we are getting Mn2 plus and 4 water molecules. So in this titration, if you see in the second partial equation, that is called the oxidation, here the Fe2 plus is converted into Fe3 plus, which means ferrous becomes into the ferric. So this is called oxidation reaction. Here the ferrous ion undergoes oxidation reaction, so that particular reagent is called reducing agent. So, and to balance this equation, right hand side equation, the another partial equation, so we need to lose one electron. Here Fe2 plus becomes into the Fe3 plus. So it becomes Fe2 plus into the Fe3 plus. It to lose one electron, so that here we have given here loss of one electron in this equation. So here we can equalize both the first part and the second part, that is the first partial equation and the second partial equation in this. Now the gain and loss of electron must be equal, so that we need to equalize this, so that we need 5 ferrous ion we needed. One permanganate ion utilizes 5 electrons, and one ion 2 plus ion liberates 1 electron only. Hence, two partial equation must apply in the ratio of 1:5, so that we have given MnO4 minus plus 8H plus 5 electron gives Mn2 plus 4H2O. So, and then we have taken the second partial equation into the, we need, so potassium permanganate needs 5 electrons to come into the to become Mn2 plus, so that 1 Fe2 plus gives 1 electron only, so that we are taking here the 5 Fe2 plus, 5 Fe2 plus gives 5 electrons. Here given the balance equation, left hand side and the right hand side equations are given. MnO4 minus plus H plus 5 Fe2 plus gives Mn2 plus 5 Fe3 plus 4 water molecule. So therefore in this reaction, so manganate ion, potassium permanganate, manganate MnO4 minus it undergoes reduction reaction, and Fe2 plus undergoes oxidation reduction. Here the reagent itself we see means, that is potassium permanganate undergoes reduction reaction, so that potassium permanganate is called oxidizing agent, and Fe2 plus undergoes oxidation reaction, so it is called reducing agent. And we shall take another example, and for permanganometric titration. So here during the oxidation and reduction, there must be, we need to identify the end point. Here in the permanganometric titration between the Fe2 plus, so here the oxidation with the permanganate and reduction of permanganate. So KMnO4 is a powerful oxidizing agent that is most widely used in strongly acidic solution. It is present in the violet color. If it is Mn, therefore the KMnO4 is it is in the violet color, that is MnO4 minus is in the violet color. Therefore we say that the KMnO4 is a self indicator. Here if it becomes MnO in the higher oxidation state into the lower oxidation state, that is 7 plus into the 2 plus Mn2 plus. Mn2 plus is colorless magnets, so that we can identify the color. The violet color, if it disappears, we can identify it. In feebly acidic, natural or neutral or alkaline solutions, MnO4 gives into Mn manganese oxide. Here the Mn oxide is manganese oxide is brown manganese dioxide solid is forming. In very strongly alkaline solution, there is a formation of MnO4 2 minus, that is green manganate is forming. This MnO4 minus is violet color. If it gives Mn2 plus, it is colorless manganese. If it gives in the feebly acidic or the neutral conditions or alkaline solutions, it gives brown manganese dioxide solid. And in very strongly alkaline solution, this permanganate gives green manganate. Here I have given another example, that is this potassium permanganate. So oxidation with potassium dichromate. Here the potassium dichromate goes into the chromium in higher oxidation goes into the lower oxidation state. Here the potassium dichromate is used as a primary standard in this titration. The indicator used here is diphenylamine sulfonic acid as an indicator. The interaction of PDC and potassium in the presence of a dilute sulfuric acid. Here in this reaction, potassium dichromate so undergoes into the oxidation reaction, that becomes into the chromium 3 plus ion. Here it is like we have balanced already in the last example. Likewise, we are balancing this equation. If we balance this equation means it needs 14 hydrogen and 6 electrons to balance the one side of the equation. So in this titration, we are titrating between there's a potassium iodide solution and potassium dichromate in the presence of dilute sulfuric acid. Here if you see in the another side of this equation, so iodine, this iodide ion becomes into the iodine molecule and it gives 2 electrons. One iodine molecules, if the two iodide ion combines and give the iodine molecule and it gives 2 electrons, but here in this oxidation reaction, so this is called oxidation reaction. Iodine undergoes this is called oxidation reaction because it undergoes loss of electron and it undergoes gain of electron. So it is, this reaction is a reduction reaction. Here 2 iodide ion gives combined and give 2 electron only, but for the one molecule of potassium dichromate need 6 electron, so that it needs 6 iodide ion to complete this equation. So that is one dichromate ion uses 6 electrons and 2 iodide ions liberates 2 electrons. Hence the two partial equations apply in the ratio of 1:3. Here that equation I mentioned here, this is the equation, the final equation we are getting in this. So this is the titration between the potassium dichromate by with potassium iodide. So in this class we have discussed about redox reactions and the principles of redox reaction, and we have discussed redox titrations with the examples, and also we have discussed about the how to determine the endpoint of the redox titrations. In this redox titrations, not and also we have discussed about the permagnometry in redox titrations. Here we have the several methods in redox titrations. And another type we have iodimetry and iodometry. Here the iodimetry, what is iodimetry? So iodimetry means reducing analyte is titrated directly with iodine. If the reducing analyte, that is the titrant, is titrated directly with iodine, then it is called iodimetry. So if an oxidizing analyte is added to excess iodide to produce iodine, which is then titrated with a standard thiosulfate solution, it is called iodometry. So its solubility is enhanced by complexation with iodide. Therefore, so we know what is iodimetry and iodometry. So iodimetry means that directly titrated against the reducing agent. If you are titrating directly against the iodine, then it is iodimetry. If the indirectly, that is in iodometry, oxidizing analyte is added to excess iodide to produce iodine. We are in the titration, we are producing iodine. So produced iodine ion is reacted with the titrant, then it is called iodometry. So we shall discuss iodimetry and iodometry in the next class in detail. Now we understood what is redox reactions, redox titrations, reducing agent and oxidizing agents, and so on. Thank you.